Okay, let's get started. Let people filter in as we go. All right, so today, last class we started talking about control, and we gave some examples about control systems, and in particular, we gave some examples about how, some fairly straightforward examples of how you can control a system to, say, minimize the cost of energy or maximize energy production, or minimize energy consumption, or maybe maximize how much energy we're storing in the case of the wind turbine, and then minimize consumption in the case of the heating system. And those sort of gave an overall feel for the kind of thing we're going to do. And we're not going to get, given that it's only 7 weeks and a third of a course, and control is an entire field of study, we're obviously not going to get that deep into this. But we're going to give look into a little bit more detail about more complex systems we can think about more complex control techniques we can use. And I'll try to give a brief overview of some of the dominant themes in control, in particular in control for smart grid systems. And so to start with that today, what I'm going to cover is I'm going to start covering in more detail certain types of dynamical systems. Remember, our overall outline here is that we want to control different kinds of systems. And to do that, I'm first going to talk about what those systems are and what kind of the problems or questions that might arise in those systems. So in particular, I'm going to start talking today, and we'll continue next time, one more lecture on dynamical systems before we get into how you control each of these things. But I'm going to give a little bit of overview on some special cases and extensions that are very common and are really good to be familiar with for that reason. So I'm going to talk some about linear dynamical systems. That's what we already saw last time, actually. I sort of motivated it saying that in an optimization task, you really want to have it be the case that our constraints are linear, so they can be convex, right? And to do that in our setting, we required that the dynamics, or required so far at least, was that the dynamics are a linear function. So the next state evolves linearly from the past state. But the example I gave was pretty simple before, right? There was just one state variable, one control input. And so really you can get into much more detail, even in linear systems, about what dynamics are there. And so we're going to start out talking a little about linear systems and about the control problems that arise there. So we're going to talk about partially observable systems. And it's the case where there's some state to a system that controls what the next state is going to be along with the control. But we may not actually know what the full state is. An example that I'll use in the class today is if you have a building you're trying to heat, for example, but you might only have thermometers in some small number of rooms, for example. Maybe not all the rooms in the building, all the hallways, etc., don't have a thermometer or a thermostat in them. And the question is, what do we do when those variables are important to the state? What the temperature is on these unobserved rooms is important. It'll affect how the rest of the building evolves. But we don't know what they are. And so how can we handle situations where we are in that scenario, where we don't see the whole state? And then finally, I'll talk about it's a little bit of a detour here, but it's really good to know, especially in the context of power systems. I'm going to talk about differential algebraic equations. And these are a particular type of dynamical system. And here, sort of taking a little bit of a diversion, we'll actually talk about continuous time rather than discrete time, just because this is the way they're always presented. And so it's good to know what these things are in the context of what you're going to see. And so we're going to talk about these. And they're particularly important for power systems because power systems, when you start thinking about actually how these things evolve over time, the power flow we talked about so far was kind of static, right? It was for an instant in time, how do these generators and these loads all balance out? When you have a situation where these things are actually evolving over time and loads are coming online and going offline without perfect knowledge of the generators, right? We don't tell a generator when we're going to flip a light switch. These types of equations govern how power is actually produced and how it ends up flowing through the network. So I think though it's kind of a more specialized topic than some of these other ones, I think it's very worth looking at a little bit for this course in particular. And then in the next lecture, also to mention, we're also going to talk about stochastic systems. And that's when you have noise in the system, though I don't think we'll get to that today. All right, so let me start off with linear systems. And the claim I made before was that linear systems we've already seen these a little bit, right? We saw the example of the heating system where we had a linear system that said how the next temperature is going to affect, or how the next temperature is going to be affected by the current temperature and the control. In this case, the control being a heater you turn on or off in the room, right? And that was kind of simple because it was a one-dimensional equation. Our constants here came from essentially physical constants, right? And the integration time step and how long of a time period we're talking about between different steps. And that is left intentionally ambiguous in these discrete time formulations. But in general, these can be more complex systems than just this one-state system. So in general, and I wrote this a little bit on the last set of slides, but maybe I'll write it again just to reinforce it here. In general, we had this evolution saying that x t plus 1 equals a of xt plus b of ut. So a determines how the past state affects the next state, and b determines how the past control affects the next state. The case we saw before, these were all single-dimensional quantities, but in general, xt is going to be a vector that we'll say is an Rn. So we have an n-dimensional state vector. And ut is going to be a vector in Rm. Again, apologies for using many, many different types of notation for what n and m are, but I'm trying to be consistent with what's used in the different fields. So when you see that, you'll sort of be familiar with it. Now, in order for this to make sense, of course, A here has to be an n by n matrix, right? Because we are multiplying an n-dimensional vector, and we want to get out an n-dimensional vector. Therefore, it has to be an n by n dimensional matrix. Similarly, B has to be an n by m matrix, right? Because we want to get out a state vector or something we can add to an n-dimensional state vector, and we're going to have m different inputs. Now, one simple extension to this, which actually, there are a lot of extensions to this thing. I'm only mentioning this one because it actually comes up in our setting when I'm talking about thermostats. There may be some additional terms you add here. I should also mention, last time I sort of got a little bit muddled in the nomenclature between affine and linear systems. We're going to talk about affine systems are essentially the same thing as linear systems. They just have an extra constant term here. And if you were listening last time, ignore what I said about affine equations. Affine versus linear is really a property of function. I was a little bit imprecise before. So a linear function of a variable is f of x equals some linear function, say c transpose x. But for a linear function, f of 0 is going to be equal to 0. So for this, for example, if x and u, without this portion, if x and u are both 0, the next state will also be 0. Whereas an affine function, this does not have to hold here. F of 0 can be some other constant amount. So it's just a little bit of nomenclature there in terms of what is affine versus linear. So one simple extension are these affine systems that we have here. And all that means is that if you have as input state 0 and as your current state the vector 0, and as output or as input the control action 0, you won't necessarily get 0 as your next state. You might get some constant amount AT. And this mattered here for the heating case at least, because the external temperature would actually affect what your system does, right? So depending on what the external temperature is, you may or may not settle to different amounts of temperature in your building. And in fact, if the outside temperature is constant, you would just, for example, settle to that constant temperature once everything got equalized, right? So here, in an affine system, you add some vector AT, which is, in this case, just to make everything work, it'll of course have to be another vector in Rn.
Is that something you can easily control, or?
No, definitely not. AT is not controllable. Anything that's controllable is put in UT. This is external factors, just like this is uncontrollable in some sense. I shouldn't use that word, because that word is very, very precise in its meaning. This you cannot directly set in the system. You cannot set the state of the system. You cannot set the state of this extra term. If you could, it would be a control action. Then it would be wrapped into this U, and then that would be what you set. All right, so we'll talk about some more examples here and about some very important questions that arise in linear systems. But as I'll mention a little bit more later and give a little bit more justification, linear systems are extremely important in control, above and beyond just systems that happen to be linear. It turns out that in analyzing a lot of systems, we end up using the theory from linear systems. So while I'll just introduce it here in terms of linear systems, a lot of what we talk about today actually applies, just with more complication, to nonlinear systems as well. Doesn't apply directly. It applies kind of in a local sense, right? Because you can approximate things maybe locally as linear systems. We're not going to worry too much about that, but just know that this theory does go beyond this case. However, it's also worth noting that this case is still quite useful, right? Because things like heating and a lot of systems do or are at least well approximated by linear systems. One thing to note is that there is a continuous time analog to these linear systems. We're going to focus mainly on the discrete case, but it's good to know that you will also see this. You'll also see the formula written as x dot equals ax plus bu, where x dot is the time derivative, as we talked about before, and this whole thing is the same. The form here is the same as it was before, but they mean different things now. Now what they mean is not saying this does not prescribe what the next state is. It prescribes how the current state changes, given what the current state is, what the control input is, how will that affect how the state changes. Now, as I said before, the easiest way to convert between these two, though it's actually not the most precise will have to do with actually a matrix exponential, it's called. But a simple way of converting between these two, in an approximate sense, is to use Euler integration. Right? So what we can see is that if we take a form like this and convert it to a continuous time, or a discrete time case, what we would get is the formula that xt plus 1 equals xt plus delta t times x dot. Right, that's just the definition of Euler integration here. I guess x dot t, just to make sure this is the derivative of time t. Now we can plug in our definition here of what x dot is from our continuous time system. So this would be a xt plus b ut. Right? And so what we see is that this equals I plus delta t, delta ta xt, right, plus delta t b ut. And so I plus a small, remember, the identity plus a small bit of this matrix is kind of like the analog for the discrete time case. That's like the A in the discrete time. And delta TB is like the B, and from the continuous time B is like the B in the discrete time. And that's a very simple way of doing this, and it's actually not quite precise. There are ways of doing this exactly, in fact, because Euler integration is an approximation. For linear systems, it actually is possible to solve these integrals exactly, to see exactly how the state would evolve. But this is sort of a first order approximation, which gives at least some intuition about what this actually is doing. Okay, and I should just mention at the end, I think I mentioned this before, but for reasons we saw last time, because linear systems, essentially in an optimization problem, are the same as linear constraints, which are ones that we know how to handle, these are often one of the few cases we can actually solve exactly. Any questions here or any of this? Okay, so let's take a little more complex example. It's really the same as the last one. It's a heating example. But we're now going to think about more than just one sort of isolated room. We're going to think about multi-room heating. Again, this is a simplified example. In general, you probably can model, or you might want to model these with more complex heat flow equations. But in the simple case, or in an approximate case at least, we can represent heating in many rooms also using a linear system. Right? And so the idea is what we saw before is that for a given room, let's talk about the temperature in a given room. From our derivation last time, we saw that the state at time t plus 1 equals the state at time t plus some constant times, where this is a constant depends on both the thermal properties of the room and the time step we're talking about. Some constant times, I'll just say the external temperature minus the current temperature, and then maybe plus some other constant times whether we turn on the heater or not. Now, the key point to see here is that this external temperature, well, that's just sort of the temperature of the surrounding area, right? So it could be the outside, but it also could be neighboring rooms. So for example, for room 1 here, it has two, so I'm using a very, very simple example here. It still is a sort of a toy example, but it's getting a little bit more complex now. We're going to talk about a building now with 4 different rooms, and we're going to talk about the state being the different temperatures in each room. The state will be 4-dimensional now. If we look at room 1, well, this same equation still applies in some sense, right? Because all that's different is the external temperature really now includes both the actual outside external temperature, maybe, from this sort of portions here, plus the temperature in rooms 2 and 3, because those also border it, so that's also going to cause some dissipation of heat through the walls. And so we also need to know about that. Now, in some sense, in a lot of actual buildings, we might be able to not worry about these things because, for example, the temperature difference here might be very small, and the insulation could be pretty good, such that all the actual dynamics here are going to be dominated by the fact that we have outside heating, or outside temperature. But as we start talking about doing things like conserving energy, right, where we actually maybe have some rooms very cold because we just don't want to put any effort into heating them if no one's going to be there, then we might actually start having some dynamics about inter-room kind of effects of how different rooms affect other rooms. Now, I do think, but having said all that, this is sort of meant to be an illustrative example, not necessarily one that is going to come up exactly like this in a lot of practice. In reality, the actual heating inside buildings is quite interesting, but maybe it doesn't quite vary at this scale. It might be very more like different zones of a building and different sort of thermal zones that can be more than just one room, perhaps. But anyway, regardless of that, again, the temperature in room T1 will evolve according to the same equation. It's just that now this external temperature isn't just the external temperature, right? It's now the external temperature on 2 sides plus room 2 and room 3 on other sides as well. So the way we can write that is that, and I'm writing it as a continuous time case here, even though we'll really solve it in discrete time. Maybe I'll just write it here actually in discrete time. So x t plus 1, the first element of that. So now I'm looking at this as a vector, considering it has all 4 rooms in it. If I look at the first vector here, well, this would be equal to xt1, right, because there's its internal temperature, plus, and I'll just, for simplicity, I suppose I should divide this by 4 to make it all work out. But I'll just say we have 2 walls where this is affected by the outside temperature, xt1. So it's affected by 2 walls there. it has one wall in contact with room T2. So it would be plus K. And T2 is a second state of xt here. So xt2 minus xt1 plus K times what happens for the third room here, right, which is xt3 minus xt1. Again, really simple examples here. It's not meant to be that realistic, but a reasonable model for how temperature might change in a building with 4 rooms like that, right? So the important part to take down, though, is that this is an equation that gives an update for what this first state will do in terms of all the past states, or at least a lot of the past states, right? But it gets a bit cumbersome to write this out. As you can imagine, I mean, imagine a building now with 4 rooms with 100 rooms, right? Writing each of these out one by one will get kind of cumbersome. So what's really nice here is that we can use matrix notation to simplify this a lot and write this in the form of xt plus 1 equals a xt plus b ut. And again, plus at, because that at there will capture this external temperature that is not sort of an actual state of the system. We'll see how this is actually done, right? For each basically, to set this up, we need to determine what these A matrices are. So we can put something like this in the form of a matrix multiplication, right? And when you do that, A will have this form here. So xt plus 1 equals xt. Now, not just for this one guy, but for all of them. Actually, let me just write this, what this is for this first one first, and you can see why this actually holds. So we can symbolize a little bit by basically saying, OK, let's separate out all the components that multiply by x, and all the components that multiply by other states, and also multiply by external states here. Right? So for xt1, which is the temperature in the first room, you have the previous state, and then minus 2k times that, because that's the term here, minus another k times that, minus another k times that. So xt plus 1, I'll just write this here, equals 1 minus 4k xt1 plus, let's find all the terms that depend on the second state here, and that would be just this one. So it would just be plus k times xt2, sorry, minus k. Did I get those? No, plus k. Right, sorry, plus k. Plus k times xt2. And then similarly, plus k times xt3. Also, plus 2k times the external temperature. And you can do the same thing for the temperature of the second room, right? Write out all the linear equations for that, for the third one, for the fourth one. And putting those all in matrix form, what you get is you get this. Now writing the delta t explicitly here, sort of wrapping that into k. I guess taking that one out of k just because I had it also written before in terms of the differential equation. Actually, you know what? I should probably actually omit these because before I had k include the delta t term here. And here I'm putting it in as well. So ignore the delta t's here. Those should probably go away. So does everyone see that this system here is now an expression for the evolution of this state, all the states, written in matrix form, right? Because when you multiply this out, you'll get, say this term here by this first row, you get negative 4k times xt1 plus k times xt2 plus k times xt3, and there's no terms that involve xt4. So this equation here is just written in matrix form, in that form we were talking about before. And I guess actually I'm leaving that xt term separately. You could easily add it there by just making this 1 minus that on the diagonals there, right? So this set of equations is a set of equations in the form xt plus 1 equals a xt plus b ut plus a t, where those things are just defined as this is a, this is a sub t, little a sub t, and this is b. Any questions there?
What was the B again?
D is what I wrote it as B here, I guess. I just wanted to separate between the actual B matrix and the yeah. Physically is how much does the heater affect evolution of temperature? It's just a constant. It depends on physical properties.
It depends on the first two.
Right. So this example here has a two-dimensional input, and the idea here is this is sort of a little bit different from our original case, because what I'm saying here is that we actually only have heaters in the first two rooms. Okay, you can only affect temperature directly in these first two rooms. So for rooms 3 and 4, this would actually be 0 here. We don't have a heater in those rooms, say, and so we can't do anything about that. And this leads to the next point and kind of a conceptual question. Yeah.
So AT here is kind of initial value or initial state of xt.
It's not an initial state, no. What it is just external factors that affect what the state is. That is a constant additional extra term here. In this case, it's just this. It's the external temperature times 2k.
Okay, so it's kind of external factors that outside of the...
Yes.
Yeah.
But do it in a affine way. They add a constant amount regardless of what xt is. So if you just had this term here without this, and xt was 0, and you add no control, so ut is 0, that means your next state has to be 0. In temperature, it doesn't really make sense, right? Because you don't want to pick somehow 0. I mean, what units do you use, right? Should these be degrees Kelvin? I don't know what they should be. You don't want to pick a temperature heating system if you have some alpha temperature. It's not 0, where your next state, if your current internal state is 0, if it was actually 0 degrees in here, it wouldn't be 0 degrees next time because there would be some external temperature that would actually affect what your next state was. So this just allows you to have the fact that 0 is not necessarily kind of a solution to this equation.
But for example, maybe we can treat like the temperature difference between internal and
yeah, you could do that certainly too, and then make sort of a delta t be your state, and that then would result in a linear system. Absolutely. So if your state corresponded not to the absolute state but to the actual difference in states, you could do that. The tricky thing there is that the actual equations are a little trickier to do there, because you have a term, right? Sort of your next state, xt plus 1, equals sort of 1 minus 4k times xt, xt1, right? So you're subtracting a lot from here, and then you're adding some external temperature, some 2k TE here. So it's not, you have to play a few tricks to get the units to work out correctly, where you can have it in a situation like that. You can certainly do it. You can sort of get this into a form where the difference is there, and so it is a linear system, right? Because if the difference is 0, then, and you take no action, the difference will stay 0. right? So that sort of makes sense here. But you have to make sure the constants are right. They have to be a little bit different from these constants we talked about before. You have to make sure the constants are right to get this situation to work. So here's now the big question. It seems pretty intuitive that if you have 4 rooms and 4 different heaters, well, you could probably eventually make the system in whatever state you want it to. Say there are heaters and coolers, right? So you can actually put in as much energy as you want in theory, or take out as much as you want. I mean, take it out, I guess. It's not how coolers actually work, unfortunately. But you could essentially, if you had sort of a full matrix here, where this was d times the density, it's pretty intuitive, right, that you could get the system to any state you wanted, or any reasonable state that you wanted. Any state if there are no bounds on UT, but if there are bounds, even maybe there's some still wide range of states you can get to. The question, though, is what if there are only 2 heaters? And so only 2 of the rooms actually have heaters in them. And let's say we can choose whatever we want, any values we want for this. We're not constrained. They can be positive, negative, whatever magnitude we want. Ignore that for now. The big question is, well, can we still get the temperature in these 4 rooms to a state that we want it to be in with just 2 heaters? The reason why this might be possible is that we can't directly affect, say we have heaters in these 2 rooms. We can't directly affect what the temperature is here, but we can indirectly affect it, right? Because the thing we turn on there will kind of diffuse into these ones. So we can have some effect over these other states. The question is, do we have enough effect over those states or not? Yeah?
For the last slide, you only took into account all the way up to T3.
Right, so the T1 doesn't border T4, so it doesn't actually depend on that. And that also shows up here because this entry here is 0.
So just because it might affect T3 and T3 affects T1, you still don't need to.
Oh, no, because it doesn't affect it in the, sort of the immediate time step. And certainly, so that's just actually one reason why it's when you write things as differential equations, but then transfer them to discrete time, this is an approximation, right? Because this is sort of exact, or almost exact, in the differential equation sense. Instantaneously, if it doesn't border that room, it won't affect it. Now, you could always say that, okay, well, at any sort of amount of finite time, there will be some effect, right? Because this one will affect, this room will affect that room will affect that room. By using Euler integration, we're ignoring that. You're ignoring that dependence, and that dependence only enters into the equation when you have multiple steps. Now, this is actually a reason, one of these sort of justification at least, or might give you some hint about why people do often prefer to work in the continuous time case. Things can be a little bit simpler there, and these things are now exact in that case. When you move to discrete time, there are often implicit approximations just in your actual differential equations themselves. In your sort of forward time equations themselves. And so some people sort of don't, that kind of is a little bit, maybe not the nicest thing, right? But in the case where you take delta T small enough, for example, or even where the thermal properties are such that these things won't change unless you have a pretty big time step, then it's a pretty reasonable approximation. And so what you'll get in the discrete time case is that the next state of this room is only affected by these 2 things. But then the state after that will be affected by the state of this one 2 times ago, right? Because this one will affect that one, and that one can affect that one. So it's just kind of a discrete approximation to what's really going on internally in terms of the actual continuous dynamics. But it's really, since we're going to be simulating this on the computer anyway, it's a pretty reasonable approximation. Again, for linear systems, you can actually do better than that. You can actually solve these integrals exactly. We won't talk about that at all. But these are differential equations that you can solve exactly without Euler integration for linear systems. And that would include that sort of effects, those effects precisely. But we're not going to worry about that here. OK, so again, big question. Can we control all the rooms if we only have 2 heaters? And this brings us to some interesting questions that we're going to ask for. We can ask them for general systems, and we can ask them for systems in general, but they are particularly interesting, or we can give particularly good answers, at least, in the case of linear systems. And so the first of these that I'll ask now is a question of what's called controllability. And this is just the formalism of what that question was that I asked before on the preceding slide. The question it's asking is, suppose I start in some initial state x1, and I want to get to some other state x star, say in k time steps. Is that possible or not? And in general, what controllability often means is actually, given enough time steps, can I get from any initial state to any other state? And it's usually thought of in terms of this sort of infinite time case. It turns out you actually don't need infinite time. You can always do it. If the system has n states, you could always do it in, you either can't do it at all, or you can do it in n steps. We won't prove why that's the case, but this is sort of just to give some idea what people will talk about when they say controllability. And really, the way to answer this is pretty straightforward. Remember, we have control. We know what x1 is. That's given to us. We can't decide what that is. But we can decide the control inputs for every time in between. So now we can just write out what the actual states are at the different times. So for example, x at time 2. And I'll go back to just the linear system here. I won't worry about the affine term. The affine term actually does not affect things here, and you'll hopefully be able to see why in a second. Affine, whether or not it's an affine term, again, in the general case where you don't have constraints on your inputs u, that won't affect the answer to this question. So x2 here equals ax1 plus b u1. Right? So the only sort of input we have there is we can pick u however we want to pick maybe x2 and going towards the good location. But as you can imagine, going back to this example here, if you only have could take one action, it certainly doesn't seem very likely that you can get the system in any state, right? Because you only have 2 knobs to turn, and you want to set 4 different values. So there's some mismatch here. You can't actually, you wouldn't be able, just sort of by your intuition, right? You shouldn't be able to get the system in any state you want to after one time step here. Now let's keep writing this though, because we don't have just one time step. We actually have k different time steps. We can pick k different control actions, right? u1 to uk. So x3 equals, again, just by definition, ax2 plus bu2. But we know what x2 equals. We'll just plug in our expression here. So this really equals ax1 plus bu1 plus bu2. And just writing out a little bit more, this equals a squared x1, right? Because we have 2 a's here. We're just going to distribute this out, plus a b u1 plus b u2. Now you can keep doing this, right? Just keep plugging this expression into the next one, and you'll get a new expression. And hopefully it's fairly obvious that the general expression is going to be x to the k x of state k rather, x at time k, equals, well, here you're going to have applied that A matrix to x1 k different times, right? So you'll have AK times x1. It depends on your, oh yes, you're right. I guess this would be, I'll write it like this just for, so it's after k steps, right? So you have to take k steps, right? So I was writing xk plus 1 here, just left it out. Yeah, so at x at time k plus 1, you will have applied a k different times. You'll have taken this guy, right, this bu, and applied a to the k minus, or a k minus 1 times, right? So this is going to be a k minus 1 times b u 1 plus a k minus 2 b u 2 plus dot 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 a b, that would be u k minus 1 plus b u k. Does this sort of chain here make sense to everyone? I'm just saying what I would, and maybe it's not, maybe I didn't really formally prove this, but hopefully this expansion is at least seems intuitive that you would in fact get this. I'm just taking the last one, plugging it into this equation, and then iterating this process. And what you get out is this. And we actually could write this in a little bit nicer matrix form here, which is just what we have here. So this equals, well, we'll leave out this guy, a, because we don't have any control over x1. x1 is given to us, remember? But then what we do control is all our u vectors. We can control not just the first one, we can control all of them. So then there's this other big matrix, a to k minus 1, b, a to k minus 2, b, dot, 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 b, times a vector of all our u's. And these are the things we can control. So now the question, at least actually conceptually, is pretty simple. The question is, can we pick this set of u's here, such that when we multiply it by this, it equals any number we want? And the criterion for that, this is sort of goes back to some of those things in those linear algebra notes that are online. But the criterion for that is that this matrix here has to be what's called full rank. Essentially, it means you can pick, I guess, n is the state dimension. You have to be able to pick n different columns here, such that you can invert that matrix. Then you set all the others u's to be equal to 0, and you pick those 4 ones to be the inverse of this thing. So maybe I'll sort of, let's see. Okay, so suppose we pick, I'm going to call this, actually this is bad, I'm going to call this sort of a script C here, this matrix. It's called the controllability matrix. That's why people use script C. Unfortunately, there's other C's in these dynamical systems, so you can't use the normal letter C, but this is like a script C there. If we can find just, say our dimension is 4, like we have in the problem. If we can find 4 columns here that are independent, we pick sort of, all the rows when we know there are 4 rows, and we pick I different columns out of this thing. This is going to be a invertible matrix, and that's the same condition as having full rank here. That's just this equivalence statement there. So if we pick 4 rows here, if it is full rank, we can find 4 rows here. I'm just calling this I, such that this thing is full rank. And then we want to say that x k plus 1 equals a x t x1 plus this times u I. And now we can start inverting things, right? So now we can say that UI, sorry for I'm running out of space here, but UI, sort of the control we're going to apply at those 4 indices is just going to be equal to C, script C, inverse, I guess I should let this, C, those 4 columns, inverse times x, k plus 1 minus a, x, 1. So again, we know what state we want to get to, we know our first state, and we can find a set of views that will get us there by inverting the matrix. And the condition, again, this is a little bit just sort of details that don't really matter too much. Don't worry about the mathematics here. The basic idea is if this thing is full rank, meaning it has independent columns, or 4 independent columns, or n for the general case of n different states, then we can just, by solving a linear equation, we can solve and determine what the u's should be that will give us any state we want in the end. Does that make sense? Yeah.
So about independent columns, is it like changing one U won't affect the other?
No, that's actually, well, so you can pick what the u's are. So they're not affected by things. The u's are whatever you want to pick. Independence is defined in those lecture notes on linear algebra that are on the course. What it essentially means is that no one of those 4 rows can be a linear combination of the other ones. Yeah.
Maybe dumb linear algebra question, but like it's not clear that if you're just taking powers of this matrix,
Yep.
like concatenating them, that you'll necessarily always get. I mean, will you expect that you get a full rank matrix?
So no, that's what depends. This is a cool question that you can answer, right?
Okay.
So you won't always get a full matrix, and this is going to be a question on the homework actually. So I'm not going to answer it here. But here's an interesting, here's what I'll tell you. I mean, the question will tell you what the answer is. So if you were to have heaters in these 2 rooms, okay, opposing rooms like this, it turns out you cannot get to any state you want. And to see this, just think about kind of intuitively what's happening here is there's no way of affecting these 2 rooms differently. Right? These will be affected in the same, regardless of what you do, you can't have sort of one effect here and a different effect there. Because these 2, so say for example these 2 rooms start at the same temperature, and you can control these thermostats however you want. You could never make these 2 rooms at different temperatures. Right? Because they're going to be exposed to the exact same conditions always. So that system is not controllable. On the other hand, if you have the things in these 2 rooms, you actually can do it, always. So the rank properties of this matrix are very dependent on the actual problem itself. And you can't say what you would expect or not expect, really. You have to just basically construct them and see what they are. And that will tell you whether it's controllable or not. And you have weird things like that, right? I mean, it kind of makes sense here because, yes, of course, you know, I can think of that example where they start at the initial state and you can't make them different. But it's not obvious to me, at least, if you had a building of, say, 100 different rooms with all different, you know, borders and different heaters in different places. It certainly would not be obvious to me whether or not you could guarantee that. And really the best way to do this is to actually just construct the matrices and check what they are. And that will tell you whether or not this is a controllable system. Yeah?
So, for solutions to use, you could have many different combinations of forms.
Yes, right. So what often happens is that if you think about k different actions here, this can be a lot more than the dimensionality of the state, especially because this is really of dimension k times n, right? Where k times m, where m is the dimensionality of your input. So if you have a very big set here, then that's actually going to be, this matrix here, C is going to be, I guess, the dimensionality of C. And I'll forget about the sort of indices here. C is going to be a n, because there's n different rows, right? Because everything is so it has a prefix of a here, so there's n rows to the matrix, times m times k, right? Because you go through k different steps here, and each time B is an n by m matrix, and so you're plugging these all together. Now, there's a good chance, in a lot of cases, m times k will be bigger than n. And what that corresponds to, again, usually, not can kind of degenerate cases here, certainly. But if this is, in fact, full rank, what will probably happen is that there are actually many more than just one set of controls that can get you from the start to the end. To find sort of the unique one, you have to kind of maybe just pick 4 random rows and solve inverted matrix and do that. As we talk about control, and actually controlling these things, what you'll often want to do is control the system doing this thing, but also pick the U's that say minimize energy, right? So you want to pick maybe like the lowest, the smallest U's that will do this. So we have some freedom in choosing U's because we typically are bigger here. And if we talk about long time horizon, we have other choices. You don't have to just do one thing to get it in that one state. But if this is not full rank, that means no matter what U's we choose, no matter how big they are, we can never control the system the way we want. Or arbitrarily, rather. We can never control it arbitrarily if, in fact, this is not full rank. So this matrix here, again called the controllability matrix, is kind of key to answering this question. Yeah?
When you say that you only have 2 heaters in room 1 and room 2,
Yeah.
and you can control the temperature and
Yep.
where you want, but like, isn't that room 3 is only controlled by room 1?
So no, because room 3 will be affected by both room 1 and the next time. So in one step, of course, you couldn't control arbitrarily. But remember, we're talking about controlling it over a long horizon of k different steps, where k is some larger number. I think in this case, actually 2 steps is enough. So what you do is you eventually say, OK, look, we can control it directly with this room. We can also control it indirectly by controlling this one time, getting this at a different level, and doing that. Now, I should emphasize, to getting this actually sort of doing it really quickly like that essentially requires you to turn on really high heat one time and then really high cooling the next time. So it's not like you can control it well. I'm not talking about kind of an elegant way of controlling it. And this will actually come up more in control when we talk about real control, because there you'll want to balance these 2 things, right? You certainly don't want to turn on the heat and then cool it just so you can do that, right? But just as a fact, and you can expect this fact by looking at these matrices here, you can in fact control it. Again, by these sort of weird sort of games you can play of turning on the heat and then on the cold and really kind of messing with it, you actually can in fact control these things. And the only way, and actually, by the way, that's very not at all obvious that you can do that. It is not at all intuitively obvious. You could not look at that system and say, yes, you can do that. The only way that I could even say that is because I constructed these matrices and looked at them. And then I know what they are, so therefore it is possible. Therefore I know it is possible. But that is really the way you determine these things. And from there, if you want, you can actually figure out what control states have to actually execute to get that effect. OK, so that's one question. Now, in general, you could ask this for any system, right? Any system, any nonlinear system. You could say, OK, can I pick controls that will have me result in some different state? But for nonlinear systems, that's a much harder problem. Linear systems have this very nice property. You can construct these kind of matrices. In the nonlinear case, you're just talking about kind of compositions of functions rather than multiplication of matrices. And it can be a much harder problem to answer. And we'll see this again, actually, some very similar thing when we talk about partially observable systems. And what happens there, can you extract the state of a system from observations? But just for now, just take it that this is nice in the linear theory and much harder to know in the nonlinear theory. Another problem, this one's a little bit more advanced. So if you haven't seen a lot of this background before, don't worry about it. I just want to mention it because it is such an important issue that comes up in linear systems, or in any system really. And this is the issue of stability. For now, as I said, don't worry about, if this doesn't quite make sense, don't worry about it. But you should at least know what the term stability means, probably. The idea of stability is, for now, let's actually assume that we have not a system we're controlling. We actually have a system plus the controller. So we have some controller ut equals k of xt. So we have a way of essentially saying for any xt, I'm going to pick my actions based on that. We can plug this into our set of equations now to get an actually kind of a what's called an autonomous system. We say that xt plus 1 equals a tilde now xt, where a tilde equals a plus bk. I'm just doing this for the sake of, it's a little, what stability means is usually defined in terms of autonomous systems, not in terms of controlled systems. So I'm assuming we have a controller here. And now the question is, let's take this system. I'm talking about linear, not affine systems here, so it's a little bit, just to clarify that. But this new system we have here says that xt plus 1 equals some matrix a tilde times xt. Right? Now obviously, if the system starts at state 0, xt being equal to 0 will imply that xt plus 1 also equals 0. So if we're in state 0, our control law says apply 0 input. And then our linear equations here say therefore you'll be also in state 0 the next time. And for linear systems at least, state 0 is kind of special for this reason, right? It's what's called a equilibrium point. If we're at 0, we're gonna stay there. Now the question is, suppose we didn't start at state 0. Would the state go towards 0 if we keep applying this control? Would this controller essentially what's called does it regulate the state around 0? So will it push the state towards 0? Maybe not exactly there, but sort of get it close to there. Or will it blow up? Will the state kind of keep getting bigger and bigger and bigger? So as an example, let's just talk about a one-dimensional system, right? And let's talk about xt plus 1 equals 5. We'll start off with a stable one. So suppose it equals 0.5 times xt. Okay? No matter how big, no matter what xt you start with, you keep applying that, xt will keep getting closer and closer to 0. It will go towards 0 as t goes to infinity. If you are at 0 already, of course, it will stay 0. But also, if you start elsewhere, it will go towards 0. Alternatively, if we have this one, that's the opposite case, right? It will keep getting bigger and bigger. You'll keep doubling what x is. And so if you start with x equals 1, you'll have x equals 2, x equals 4, 8, etc. And so you'll make this very big. And in general, those are kind of the only two possibilities. I guess you can also have kind of right on the boundary here, where xt plus 1 equals xt, and then it's sort of just barely on the boundary between stable and unstable. But so I guess these are really the three possibilities. It can go to infinity. It can either say that xt goes to 0. You can have xt goes to infinity, or xt just doesn't do either of these. It just stays what it is. And the question is, So this is pretty easy for a 1D case, right? Basically, if this is the A matrix in this case. And so this case happens whenever the absolute value of A is less than 1. Right? You can have a negative here too. It'll just flip the signs in successive iterations, but it'll still, in magnitude, go to 0. This case happens whenever A, the magnitude of A, is greater than 1. In this case will only happen when the absolute magnitude of A equals 1. So this is a pretty simple case here for the 1D case, right? It's just, look, if you're making it smaller, guess what? It goes to 0. If you're making it bigger, guess what? It grows, right? It goes to infinity. If you're not making it either, it stays the same. Not that deep here. The answer in the general case, where you have multidimensional state vectors, it looks more complicated, but it isn't really that much more complicated than this. All it depends on is what's called an eigenvalue decomposition of this matrix A. So this is the part where I'm being a little more advanced here than the rest of the course. None of the rest of the course requires eigenvalues. But if you've seen this, I mean, they are in the notes, the linear algebra lecture notes, so you can read it. I'm not going to explain what these are in a lot of detail. All I will say is that you can take any matrix A, or not any matrix, but most matrices, we'll say, and factor it into the form of some matrix S times lambda times S inverse, where lambda is diagonal. In fact, this can be a little bit complicated because for general matrices, this can actually be, even if this is all has real numbers, these can actually all be complex valued. So you need to actually allow for complex entries in here for this to be doable for a lot of cases. And some matrices, you actually can't even do this quite right exactly. You have to use a slightly different form, but let's take it like this. The nice thing about this is that what really matters in some sense for stability is the different powers of this matrix A tilde, right? Because x, if you start at x1, it's like we did before, x2 will equal A x1, x3, sorry, A tilde x1, x3 will equal A tilde x squared x1 dot, point where xt equals A, I should say xt plus 1, equals A to the t of x1. And the nice thing here is that because we're not having controls sort of explicitly written out here, this is a very simple form. We don't have to worry about all the controls here. We're just going to factor those all in, and so that's all taken care of in this A tilde matrix here. So all that really matters in some sense is the multivariate generalization of this, right? Does A to the t as a matrix, does that have entries that go to infinity, or does that have entries that stay at sort of a reasonable range? Or actually, go back, they either will go to infinity much like this, or they will go to 0. Or they will stay 1, but that's kind of the very, very boundary case. And the answer for that question can be figured out from the eigenvalue decomposition. So again, just very, very briefly here, what you do is you take A to the k. That's just these eigenvalues times each other many times. The cool thing about the eigenvalue decomposition is that these things cancel, right? You're saying it as S in the beginning and an S inverse on the end. And so these S times S inverses cancel. And you wind up with S times lambda to the n times S inverse. Now, a diagonal matrix, when you take that to a power, it's actually quite easy because you can just take the individual entries of that matrix and raise them to a power. That's how a diagonal matrix, you can just try this out actually if you want. Because diagonal matrices only sort of scale the individual rows and columns, if you take a diagonal matrix to some power, that's just equal to each of the individual elements on the diagonal raised to that power. So, in some sense, those eigenvalues, which are these values on the diagonal of lambda, those are acting like this term here, this scalar term here. And if those eigenvalues are bigger than 1, it will go to infinity, even if 1's bigger than 1, by the way. 1 being bigger than 1 has has the power to make the whole matrix go to infinity, because you're still pre-multiplying by s and post-multiplying by s inverse. So once you do this, everything goes to infinity. Whereas if they are all less than or equal to 1, or sorry, strictly less than 1, this will in fact go to 0. If any one is equal to 1, then you sort of stay in this boundary case here, and it'll never vanish entirely, but you won't go to infinity either. So again, this is not, if you didn't quite follow this is using some linear algebra, which is substantially more advanced than the rest of this course. So don't worry about that. But the idea of stability here is important. It's saying, will my state blow up or will it go to 0? And that can be answered. The takeaway, I guess, is that can be answered by looking at the eigenvalue decomposition of this and checking whether those are more or less in absolute value than 1. Again, this can be complex too. So you have to use sort of the eigenvalues can be complex actually. So you have to use actually the the absolute value of these things in the complex case as well. What's the length of those complex vectors? But that's the rule. This is how you determine whether a system is stable or not. All right, in the little bit of time we have left, and I guess we didn't get all that far, I'll try to speed up a little bit because I want to get to not only these things, but also how you control these things. So we'll try to go a little faster next time. I will mention, though, I mentioned this at the beginning, but saying it again, there are lots of uses for this theory beyond just linear systems. And the most, one of the most obvious ones is actually when if you take a nonlinear system and look at an equilibrium point of that nonlinear system. And so what this is, remember, for linear systems like this, 0 was an equilibrium point, because if we started with 0, we would end with 0 as well. Now take sort of any equilibrium point here, just some u star, some x, gives you back x in the end too. It means we can keep applying these, it won't change the state. And if we look at the Jacobians of this function around this point, where a is the Jacobian with respect to x, and b is the Jacobian with respect to u, it turns, and I won't prove this at all, I won't prove this, it's actually not that easy to prove. Well, it's sort of easy to prove, I guess. But it turns out that the controllability and stability of this nonlinear system around that point, in a local ball around that point, those are determined, not approximately, but exactly, by the stability and controllability of these matrices here. Now that ball can be arbitrarily small depending on how crazy that function is. But for some ball around that equilibrium point, so for some neighborhood of points around this point, you can say for sure this is stable, or this is controllable or uncontrollable, stable or unstable, or controllable or uncontrollable, based entirely on analysis of these linear systems. Which is a really, really powerful statement, right? This is incredibly powerful to be able to do this. And you can do it using linear system theory. So again, we're not going to prove any of that, but I'm trying to highlight the fact that these things are useful just beyond linear systems, because there are nonlinear systems in the real world, and these techniques are very useful for those as well. All right, so getting started with this one last topic before we end now. Linear systems was a special case of the general dynamical system, a very useful special case. Now we're actually going to talk about a generalization of the system, so a more general class of systems. And these go by the name of partially observable systems. So the implicit assumption in some sense, or I guess it wasn't quite an assumption yet, but a property of a lot of the control we were talking about before. Model predictive control, or not, sorry, I didn't use that term yet, but the control as optimization, where you get your current state, you know what the dynamics are, so you simulate forward, all this kind of stuff. A big assumption of doing that was that you were actually able to know your current state, right? Because you had to start somewhere. That was one of the constraints that we had last time, remember, what the state was. So we actually have to say, okay, we know our current state. It's x0 or something, x initial. But it turns out, just the way you can't always control every state, sometimes you can't observe every state. You can't actually know what the state value is, all the values of the states are that you really care about. And this is in fact so common that almost all real, or I take that back, but a whole lot of real systems are in this class. Actually, a great example is, which doesn't have to do with energy, so I won't spend too much time on it, but if you're flying a plane, for example, and you want to know your position, maybe you don't have your position globally, all you have is a distance reading from some beacon that you can see. So obviously that depends on your state, but it doesn't actually tell you what your state is. And in fact, you can't even invert that function. If you just have one beacon, you can't even invert that function to know what your state is. If you have three, you can. Right, this is triangulation. But if you only have one beacon, you can't do it. So again, don't worry about that example. That's sort of giving examples of cases where you might not know your full state. The example we're going to talk about here is if you have that same sort of heating case, but you only have thermometers in 2 of the rooms. Much like we can only control 2 of the rooms with heaters, what if we only have thermometers in 2 of the rooms? And so in general, what this will take the form, the system take the form of the following. We have, as before, our dynamics of the system. So xt, as before, equals xt plus 1 equals f of xt ut. That part doesn't change at all. So if we know our initial state and everything's deterministic, because that's not very hard at all, because then we can just simulate forward, so we're fine. But what we get instead of observing xt at every time, what we observe is some other quantity yt, where yt is some function of xt. Right? So in the case of the thermostats, maybe this is just a subset of the actual ones. In the case of the beacon for flying a plane, this would be a function of the current state and the location of the beacon. It's actually a nonlinear function there, right? Because it would be the square root of the distance between those, or sorry, the distance between those two. But the point is that we don't know xt. All we can see is yt. And yt in general, so let's write this here. So we're going to say that yt in general is going to be p dimensional. We need another sort of length here. Sorry about that, but we just do. And that equals h of xt. So h is really going to be a mapping from Rn to Rp. And typically the implicit assumption here is that this is a non-invertible mapping. Right? So either we have p being less than n, typically that's the case. Typically p is less than n. And what that means is that this isn't as if we can just determine what x is from a single y. If that was the case, I mean, I guess we could use this formulation, but in the deterministic case, it would be kind of silly because we might as well, if we can determine what x is from a single y, there isn't that much interesting going on here, right? We just basically do that before we get our observation, and we just treat it as if we can observe the real state. So typically, we'll assume that the dimensionality of our observation is less than the dimensionality of our state. You could also have this for nonlinear systems. You could also have it where, or actually for any system, you could have this be the case that this was bigger than or equal to. It just still was not an invertible function. So maybe you get redundant information in your measurements that doesn't help you determine what the state is. But the basic point is you cannot determine the state from just one observation. And just like a big question for control was this controllability question, the similar question for partially observable systems is called the observability question. And that is, if I am given a sequence of measurements, so say I know from y1 I can't determine what x1 is. But what if I'm given y1, y2, y3, up to yk? Can I determine x, and I guess x1? And in fact, because this is deterministic, if I know x1, and I know all my controls, I will know all my x's. So can I go from this to know all my x's here? Again, you can't do it from one, but maybe you can do it from more than one. This is sort of the same intuitions we had with the heating system, right? Because for controlling it, right? You can't affect all the states in one time step, but maybe you can in two. And similarly here, if you observe thermometers in 2 rooms, for example, over many time steps, maybe you can figure out what the other rooms had to be in order to get those readings that you're observing right there. And in fact, I won't go into this in much detail in this course, but there is this very, very nice what's called duality between the controllability question and the observability question. And it turns out these are actually answered in almost the exact same way. You construct very, very similar looking things to do this. In the linear case, in the nonlinear case too, but these are both hard in the nonlinear case. So what we're going to do next time is we're going to talk about, first of all, how might you solve this in the general case, right? You could maybe say, okay, I'm going to use general functions here. Can I determine what my state x1 is given a lot of general nonlinear observations? And that will be something like Newton's method, but we have to use to do that, because these will be nonlinear equations now, and so we'll have to use something like Newton's method to actually get this answer to this question. For the linear case, things can often be a lot nicer, and we actually can answer questions. Just like with the controllability question, we can come up with better answers to this. For the linear case, which I'll talk about shortly on Thursday, we'll talk about how we can answer questions like this. Okay, so the last thing is remember the milestone for the projects is due on Thursday. So please get that in. It's a maximum of 2 pages. It does not have to be 2 pages. It can be less than that. I just want to know that you have made some progress since the initial proposal and that you are on the right track. It is much more for your own sake to get yourself on the right track than it is for me to evaluate these things yet. It counts for a relatively small portion of the grade, so the important part is to get it in more than to have it be perfect. But I will see you on Thursday.